Hello everyone, welcome to Digital Communication Tutorials. In this video, I'm going to take up the second numerical on detection and estimation. Please note once again this is a numerical on drawing the constellation diagram. Let me read out the question first. Consider the set of signals Si of t equals square root of 2e by capital T into cos 2 pi fct minus I into pi by 4 for t varying from 0 to capital T and 0 otherwise, where I equals 0, 1, 2 and 3 and fc is an integer multiple of 1 divided by t. Part A of the question says determine the dimensionality capital N of the signal set. Part B of the question says determine a set of orthonormal basis functions to represent this set of signals. Part C of the question says determine the coefficients Sij of the signals Si of t. And lastly, part D of the question says give the signal constellation diagram. Right, let me start with the solution part here. Let me rewrite the given equation for Si of t. Let me call this as equation 1. Now we look at the equation part here, which is in the form of cos of a minus b. So I'm going to use a trigonometric identity for cos a minus b, which is given by cos of a minus b equals cos a cos b plus sin a sin b. Using this trigonometric identity, I'm going to expand equation 1 Si of t equals square root of 2e divided by capital T into cos of 2 pi fct into cos of I into pi by 4 plus square root of 2e divided by capital T into sin of 2 pi fct into sin of I into pi by 4 for I is equal to 0, 1, 2 and 3. Let me rewrite this equation taking cos of I into pi by 4 as the first term along with square root of 2e by t. Right, let me call this as equation 2. Now, the part A of the question says to find the dimensionality capital N of the signal set. To find the dimensionality, now we are supposed to expand the equation Si of t by substituting I is equals to 0, 1, 2 and 3. Let me do that. I'll start with I is equals to 0. So, S is 0 of t equals square root of 2e divided by capital T into cos of 0 into pi by 4 is still 0 multiplied by cos 2 pi fct plus square root of 2e divided by capital T into sin of, once again it is 0 multiplied by pi by 4, it is 0 into sin 2 pi fct. In a very similar fashion, I can write the remaining 3 equations as right. To find the dimensionality, we have to identify the parts of this equation which are common among all the 4 equations. If you look at this very carefully, you will find that in the first component of each of the equations, square root of 2 by t into cos 2 pi fct is common, and in the second component of each equation, square root of 2 by t into sin 2 pi fct is also common. Please note that you cannot take energy of the signal E as a common component. Only the common components are square root of 2 by t cos 2 pi fct in the first component of each equation and square root of 2 by t into sine of 2 pi fct. Therefore, we can now say these components form the basis function. As I said, the first basis function is phi 1 of t is equals to square root of 2 divided by capital T into cos of 2 pi fct. This is defined over the interval 0 less than or equal to t less than or equal to capital T. And the second basis function is phi 2 of t is equal to square root of 2 divided by capital T into sine of 2 pi fct, which is also defined over the interval 0 less than or equal to small t less than or equal to capital T. Now, you must note that a orthonormal basis function must have the property of having an unit energy, and the two basis functions should be orthogonal to each other. Only when you take the basis functions as shown in this set of equations, which I will call it as equation 3, they will satisfy the condition for orthonormality. If you take E, which is the energy of the signal component, as a component of the basis function, then they will not be orthonormal. Right. So, having found the number of basis functions, we can now confidently say the dimensionality of the signal set n is equal to the number of basis functions, which is equal to 2. Right. That is the answer for part A of the question. Going back to part B. Part B of the question says determine a set of orthonormal basis functions to represent this set of signals, which we already have done because equation 3 represents the orthonormal basis functions themselves. Then we move on to the third part of the equation, which is to determine the coefficients Sij of the signals Si of t. To understand this, let me write the equation. We know that any signal Si of t is represented in terms of its coefficients as summation j varying from 1 to capital N Sij into phi j of t. If you come back to the equations that we have written here, which I will mark it here saying star, you will note that every single equation is written in the form of a coefficient multiplied by phi 1 of t plus a coefficient multiplied by phi 2 of t. Therefore, the equations shown with star here are nothing but the expansion of every single component of the signal written already in terms of its coefficients. So, to obtain the coefficients Sij of every signal Si, all I have to do is to simplify the component of cos I into pi by 4 and sin I into pi by 4. That would be the coefficient. However, you should not forget the square root of E, which is also a coefficient here. So, I can now write S0 of t as square root of E into cos 0 multiplied by phi 1 of t plus square root of E into sin 0 multiplied by phi 2 of t. Let me write that. Therefore, this simplifies to square root of E into cos 0 is 1 into phi 1 of t. Right? The second component is anyhow 0 here. Therefore, the coordinates of the signal S0 of t in the signal space can be given as S0, which is the signal vector, equal to square root of E comma 0. Moving on to S1 of t, we have square root of E into cos of pi by 4 into phi 1 of t plus square root of E into sine of pi divided by 4 into phi 2 of t. We know that cos pi by 4 and sin pi by 4 are equal to 1 divided by root 2. Therefore, this simplifies to Therefore, the coordinates of the signal vector S1 would be square root of E divided by 2, comma square root of E divided by 2. Moving on to the third equation, S2 of t, which is given as square root of E into cos of 2 pi divided by 4 into phi 1 of t plus square root of e into sine of 2 pi by 4 into phi 2 of t. This is equal to therefore, the coordinates of the signal vector S2 are given by 0, root e. Lastly, we move on to the last signal component S3 of t. This is given as square root of e into cos of 3 pi by 4 into phi 1 of t plus square root of e into sine of 3 pi by 4 into phi 2 of t, which is therefore, we can now conclude the signal component S3 of t can be represented as a vector S3 with coordinates given by minus square root of e divided by 2 and plus square root of e divided by 2. Right. So, with that, we have now found the coefficients Sij of each signal Si of t for I varying from 0 to 3. That completes part 3 of the numerical. Lastly, we now move on to the part 4 of the numerical, which is to draw the signal constellation diagram itself. Let us start with the signal constellation part. We know that there are two basis functions, therefore the signal constellation is going to be a two-dimensional diagram. Let me start with the x-axis here. This will be phi 1 of t axis and we have the y-axis. This will be phi 2 of t axis. Let us come back to the coordinates for S0 of t, which is actually the signal vector S0. You see that it has a coordinate equal to root e comma 0. That means it is located at a distance of root e on the x-axis. So, I will mark it here. This is S0. Come to the S1 equation. It is plus root e by 2 comma plus root e by 2. So, it will be somewhere here. S1 I will call it as it is plus root e by 2 comma plus root e by 2. Then moving on to S2 of t, it has a coordinate equal to 0 comma root e. So, it will be at a distance of root e on the y-axis. And lastly, we have S3 which has a coordinate equal to minus root e by 2 comma plus root e by 2. So, it will be located here. So, this is S3. Right. So, that is the constellation diagram for the given signal set. That completes the part 4 of the numerical as well as the complete numerical itself. Right. So, that's about this video. If you liked this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.